Right. Hello everyone, thank you very much for coming. My name is Gordon Brown. I'm a senior software engineer at CodePlay Software, and I'm going to talk to you today about SYCL. It's a C++ programming model for GPUs. Originally this talk was written by myself and Michael Wong. Unfortunately, due to a scheduling collision, Michael won't be able to attend because he's arriving at the conference tomorrow, so it'll just be myself. So the talk should be around 50 minutes, so there should be plenty of time for questions at the end. So, brief introduction about who CodePlay are and what we do. So CodePlay, we're a company, about 70 of us in Edinburgh in Scotland, and we develop heterogeneous solutions based on open standards like OpenCL, SYCL, Vulkan, HSA, standards like that. So we develop like compilers and runtimes and other tools for quite a few different domains, including like automotive, vision, HPC. So a little bit about myself. I've been at CodePlay for about 6 years now. That time I've been working on SYCL since its first inception about 5.5 years ago. Over that time, I've been working on Compute CPP, which is CodePlay's implementation of SYCL, as well as contributing to the Khronos SYCL group standard. In the last couple of years, I've also been working with the ISO C++ standard on in the SG1 executors and heterogeneous groups. And I'm sure most of you know who Michael Wong is. He used to work at IBM. He's now at CodePlay as our VP of Research. He used to be the CEO of OpenMP. He's now the chair of the SYCL group, as well as many ISO C++ groups, including the new directions group. So to give an overview of what I'm going to be talking about today, I'm going to start off with a little motivation of why you might want to program for a GPU. And I'm going to follow on with a crash course in GPU architecture and GPU programming model. Then I'm going to kind of give you an overview of what SYCL is, and then dive into an example of writing a GPU algorithm, a parallel reduction algorithm on a GPU using SYCL. So many of you have probably heard phrases like free lunch is over, the end of Moore's law, the future is parallel. I'm sure many of you have seen a graph that looks a little like this many times, showing the clock speed of CPUs over time and how it's reached a point where it's no longer steadily increasing anymore. So I'm not going to go into a great deal of detail about it. There's been many talks in the past that have covered this in a lot of detail. But I think the important thing to take from this is that while CPU architectures are still developing and improving over time, it's generally accepted that more performance in the future will largely come from parallelization, whether that be thread parallelization or SIMD vectorization or just dispatch to heterogeneous devices such as the GPU, which is what we're going to talk about today. And the important thing to note is that GPUs are everywhere now. So everything from like mobile phones to laptops, tablets, desktop PCs, even cars have GPUs. So going into the future, everything you program for will have a GPU or some other heterogeneous device they may want to program for that's not a CPU. So it's important that as C++ developers, we learn how to sort of learn the architecture of these devices and how to program for them. So to take a quick example, consider a typical Intel chip. This is the Intel i7 7th gen. So this has 4 CPU cores, each with hyperthreading, and each with 8 wide AVX instructions, and it has integrated HD graphics with 1280 processing elements. So if you're only writing sequential C++ code, you're only taking advantage of a very, very small portion of that chip. Right? There's a lot of the chip that you're not taking advantage of. But say you write your code in a way that the compiler can optimize to use vector instructions. So compilers are very good at now at what's called like automatic vectorization. Which say if you write your code in a particular way with the right optimizations, compilers can automatically vectorize your code to make use of SIMD vector instructions. And then say you take advantage of multi-threading. So you, C++, out of C++ 11, you can now query how much hardware concurrency your system has. And that tells you effectively how many threads that you can run concurrently. And you can use that to launch SID threads and take advantage of all of the cores that you have in your chip. But there's still a large part of this chip here that you're not taking advantage of, and that's the GPU. So by not also taking advantage of the GPU and dispatching work to the GPU, you're leaving a lot of performance on the floor that you could be using. So GPU programming, GPU used to be like a very niche technology. It used to be restricted to particular domains, and this was largely because of its complexity. It was generally very verbose and very low-level APIs to work with. It was generally separate source, which means that your host CPU code and your GPU code were generally written in different source files, often in different languages. And a lot of things that you kind of take for granted in C++, of having like standard calling conventions for, copying arguments to your function, setting your arguments, that kind of thing. That's all very explicit in these APIs. You have to call explicit API calls in order to do all of that. So a simple hello world with something like OpenCL would require like this long 12-step process, which would look something like this. And that's just to do a simple like adding numbers together into arrays. And that was a very high learning curve. It was very difficult, it was very error prone, very difficult to work with. But that's not the case today. So there are many modern C++ programming models and languages that let you do this in a way that the average C++ developer would be more familiar with. Just to list a few, there's C++ AMP, there's SYCL, there's CppCon, Khronos, HPX, Raja. These all target, say, different domains, do slightly different things, but they're all effectively doing the same thing. They're allowing you to program heterogeneous devices such as GPUs using a familiar C++ programming model. And in all of these models, you have what's called a single source model, where your host CPU code and your device code are both in the same source file. They're both C++. Generally, your device function is a lambda. So it's a lot more accessible to the average C++ developer than what we used to have. Another thing to consider is that GPU programming, as well as execution on a lot of other domains, is being standardized now in C++ executors. So this is something that's not available now, but it's in the works and it'll be available sometime in the future, maybe C++ 20, 23. And what this means is we're standardizing the way you execute work. So you can write code in a generic way that can then be targeted at a range of different systems, such as multi-threaded like thread pools, or GPU, or some other heterogeneous device, or a network device. So this is all being standardized. Okay. Okay, so the next part I'm going to look at is a look at the GPU architecture and the GPU programming model, so you can sort of understand how that works. So at a very high level, the difference between a CPU and a GPU is the CPU has a small number of very large processors, and it has a lot of control structures which allow CPUs to be optimized for latency. So you can get your tasks can run as fast as possible. However, this requires quite a lot of power. GPUs, on the other hand, have a large number of very small processors, less control structures. It's a less flexible program. There's less you can do. There's more restrictions, but requires a lot less power, and it's optimized for throughput. So it's optimized for doing a large amount of work in a small amount of time. So to have a little look at the way a CPU and a GPU interact. So you have your CPU, this is often called the host, and then you have the GPU, so co-processor of the CPU, this is often referred to as the device. And then you have the CPU and the GPU both have their own discrete memory which can communicate with each other. So the GPU is described as a co-processor of the CPU in that it doesn't have a main function that executes in the same way that a CPU does. It has to be invoked by the CPU. So the way this would normally work is, so you have, first you allocate memory on the GPU from the CPU. And then the CPU copies memory data into the GPU memory. And then the CPU will invoke what's called a kernel. Kernel's a GPU function on the GPU. And once that completes, the CPU will then instruct the GPU to copy the data back. Okay. So, quick summary of the CPU. I'm sure everyone's quite familiar with this. So, CPU has a region of dedicated memory, so it's DDR, connected to the CPU via a bus. Then you have a number of cores, and then you have a number of layers of cache, generally like L1, L2, L3, which can vary. And then on each core you have a number of registers. Then if we look at the GPU works slightly differently. So the GPU also has a dedicated memory, we call this global memory, and this is also connected to the GPU via a bus. And then inside the GPU, you have a number of what are called compute units. And there's generally quite a lot of them, but I've only drawn 2 here just to make the diagram easier to visualize. Each one of these compute units has a dedicated region of memory called local memory. And inside each one of these compute units, there's a number of processing elements. And each processing element also has its own dedicated region of private memory. And in a moment, I'll go into this in a bit more detail and explain how these different memory regions behave and how the processing elements execute work. So, a processing element executes what's called a work item. So a work item runs on a processing element. A work item is effectively like a thread. You can think of it like a thread. And each work item can access the private memory of that work item's processing element. And then your work items are grouped together into work groups. And a work group essentially runs on a compute unit. And all of these work items within a work group can access the local memory that is local to that work group, or that compute unit. And then finally, when you launch a kernel, you launch a large number of these compute units. And all the work items and all the work groups can access the global memory available to everyone. So the important thing to consider here is that private memory is local to a work item, and this is generally very, very small. It's very, very low latency, so it's very fast to access, but it's very small, so it generally only has space for registers or stack space. Local memory is larger, but it's shared across your work items. This is generally used for sharing partial results between your work items during your computation. But it's also quite low latency, quite fast to access. And the GPU is much, much larger. You'll tend to have a lot more, global memory is much, much larger. You tend to have a lot more space in global memory, but the latency is far, far higher. So it's very expensive to access memory from global memory. Yep. So let's take a look at how the work items actually execute. So on a GPU, you'll have a large number of work items executing concurrently. But not all of the work items will execute uniformly. So some work items will execute once and then other ones will execute later. So most GPUs execute in lockstep, which means a number of work items will execute together. And this is because the way the GPU executes, generally it will load as an instruction once and then execute that instruction across what's generally referred to as a warp or wavefront. So it's a number of work items will execute together with the same instruction. So what you can do a GPU, you can communicate data between work items. So you can share partial results between work items using local or global memory. Generally, it's preferred to use local memory because there's a lot lower latency. It's very expensive to communicate via global memory. But this can lead to a problem in that if there's no guarantee of which work items will execute in which order. So if you have one work item, say this one here, that's waiting on the result of another work item that may not have run yet, may not have written this result, then you end up with a data race. So depending on which work items execute first, you may or may not have the result there yet. So the solution to this is that you have what's called a workgroup barrier. So you insert this barrier, which essentially means that all work items in the workgroup must wait for all other work items to finish before it can continue. So here, all of these work items are in the same workgroup, which means they will all write to these values in local memory before continuing. So then there's no data race. However, you have to be careful because this doesn't work across workgroup barriers. So if you're having one work item store a partial result on data that will be accessed by another work item on a different workgroup, there's no guarantee that that workgroup will even started yet. So again, you have a data race. So in this case, you need to use a kernel barrier. So kernel barriers are implicit barriers that are in place between kernel invocations. But these are, you should tend to avoid these as much as possible because it's a lot less efficient. Because local memory is not persistent between kernel invocations, you can only share data between global memory, which is a lot higher latency, and also the overhead of launching multiple kernels can be quite expensive. But if you do this, then the same thing happens again. You can guarantee that all of these work items will finish before you launch your next kernel and continue running. So to summarize, the GPU programming model is effectively layers of work items, synchronization primitives, and memory regions. So a work item is collected, work items are collected together into work groups, and a kernel executes multiple work groups together. Work groups can be synchronized using workgroup barrier, and kernels can be synchronized using kernel barriers. And each work item can access its own private memory, the local memory of its work group that it shares with all the other work items in its work group, and global memory. So how do you actually write GPU code? Right? So you have to think about things slightly differently from the way that you'd write CPU code. So when you write CPU code, say if you wanted to square a number of values in an array, you could just write a simple loop that would iterate over all the elements and square each value, put it into the output array. But all of this is still running in a single thread. There's no parallelism here. You're doing everything in one thread. However, when you're writing code for a GPU, you follow a model that's called SPMD. So it's a single program, multiple data. So you write your code as if it was a sequential program, as if it was the code within some loop. So you write your code as if this was one iteration of a loop. And then that function needs to know essentially which index of that loop it's in. So you write your code with the knowledge that you're going to be launching that function multiple times in parallel. So say you do this, so these would be equivalent things here. So you call that function with the same inputs, but you specify how many iterations of that function you want to run. So when you launch a kernel on a GPU, you specify what's called an ND range. So an ND range effectively describes the number of work items and work groups that you want to execute on the GPU. So this is made up of the global range, which is the total number of work items. So in this case, it would be 12 by 12. And then the local range, which is effectively the size of each work group. And those have to be uniform. So the global range 12 has to be has to divide into the local range. And then this ND range of work groups and work items will then be mapped to the hardware, so to the compute units and the processing elements of the GPU. So this one won't always map directly, so it depends on how much work you're executing and how much compute units and processing elements your GPU has. So if you're requesting much larger ND range than your GPU has, then each processing element, each compute unit will do multiple work and it will just run more one after the other. Well, obviously, if you're requesting an ND range that's smaller than what your GPU can do, you're not taking full advantage of what your GPU can do. There'll be processing elements that are just sitting idle, not doing anything. So, like in the example before where we had this ID that told you which index you were in your function, when you're running in a kernel, you need to know which index you are within the ND range that you've just specified. So there's a number of things that you can query within a kernel to know where you are. So the first one is the global range. This tells you the full range of work items. So in this case, it would be 12 by 12. The next is the local range. So that's like the range of work items of the work group that you're in. So here it would be 4 by 4. Then you have your group range, which is effectively the range of groups that you have. So in this case, it would be 3 by 3 because you've constructed 12 by 12 work items into 4 by 4 groups. So you have 3 by 3 groups. And then you have your global ID. The global ID specifies the current index into your global range. So here this would be 6 by 5. And then local ID is the current index into your local range, which in this case would be 2 by 1. So it's within this yellow box here. And the group ID would be your current index into the group. So this would be 1 by 1. Before going on, I should note that the terminology I've used here is specific to OpenCL and SYCL. So if you were working with CUDA, the terminology might be slightly different. The terms don't always match, so that's something to be aware of. Okay, so what is SYCL? So SYCL is a standard from the Khronos group. So the Khronos group is a consortium of companies that work together to design standards that vendors can implement and users can program to, similar to ISO C++. And the Khronos group do a lot of different standards like OpenGL and Vulkan, and one of them they do is OpenCL and SYCL, which we're talking about now. And SYCL is a single source C++ programming model for GPUs and other heterogeneous devices based on top of OpenCL. So you get the performance portability of OpenCL, being able to write programs that target a number of different devices, including GPUs. But you also get the benefit of standard C++. So some of the benefits of using SYCL. So SYCL enables programming heterogeneous devices such as GPUs using standard C++. And the standard part is quite important. I'll cover that in a moment. But it provides a high-level abstraction over a lot of the boilerplate code that you would have to do in something like OpenCL. That it covers a lot of the things that you don't want to be concerned with. It also goes beyond that, and it has efficient data dependency analysis, which allows you to describe your work in terms of dependencies for your kernels. So then it allows the runtime to do a lot of very clever things in terms of scheduling your kernels and copying data for you. So it makes programming a GPU a lot easier and iteration over your algorithms a lot easier. So this is what the SYCL ecosystem looks like. So the way this generally works is you'd have an application, maybe some algorithm that you want to write on a GPU, and that would generally be in some template header. In that algorithm, you would write some code using the SYCL for OpenCL API, and then when that compiles in, that runs on top of OpenCL, and then targets a number of different OpenCL-enabled devices, including a GPU. So one of the things that we wanted to do when we were defining the SYCL standard was that there are many other APIs for programming GPUs using C++. But many of them have a problem that they're not standard C++. For example, if you're programming in CUDA, you need to have this global or host keywords to specify whether your kernel's for the device or host. You also have to have this non-standard syntax of the triple ankle braces around kernel invocations. For OpenMP, you need to use these pragmas. C++ AMP, you have a similar keyword, restrict. In SYCL, we don't have any of these. SYCL is just completely standard C++. So any SYCL kernel that you write can target a range of different GPUs, but it can also run, even if you don't have a GPU in your system, you don't have OpenCL, you don't even have a SYCL compiler, it will still compile and run on standard C++ using the SYCL runtime. And furthermore, SYCL also provides what's called a host device, which is effectively an emulated OpenCL device, which means that the programming model that we were just looking at, those same guarantees are made by the host runtime, which means that you can debug your algorithms as if you're running on a GPU, but you're actually running it on the CPU. Which can be very, very useful because GPU debuggers are very difficult to come by, and they're very, very difficult. They'd be very, very difficult to use. So, and one of the other main features of SYCL is the way that it handles data. So it has this quite unique way of handling data where the storage and access of data is separated. So you have buffers which manage data and accessors which give you access to data. And this allows the runtime to do a lot of very clever things in terms of data dependency analysis, of scheduling tasks, and copying data efficiently. So to give an example of this, so if you have a buffer manages data across host and one or more devices. You can then create an accessor, and the accessor is type safe, and the accessor has certain properties which describe how and where you want to access the data. So you could have multiple, these are command groups, so in SYCL a command group represents a kernel that you're executing on the GPU. And you can have multiple command groups that are all accessing the same buffer, perhaps in different memory regions with different read-write access privileges. And this gives a lot of information to the runtime to be able to do a lot of the underlying management of the data and the execution of your kernels efficiently. So one of the properties the accessor allows you to specify is where you want the data to be. So as we saw before, there are quite a few different memory regions on a GPU where you can put your data. So first of all, you can ask for host access to the buffer, which gives you immediate access to the data on the host on the GPU at all. And then you can ask for a global accessor. That gives you access to the memory in the global memory region. And you can also ask for a constant accessor. So that gives you access to the same memory, but in constant memory region. So constant memory is, we didn't really touch on that, but constant memory is a portion of the global memory that is read-only. So a lot of GPUs can give you more efficient access if you guarantee that you won't be writing to it. And finally, we have a local accessor. It works slightly different in that it doesn't use a buffer, because what a local accessor does is allocate memory in local memory for each of your work groups. So to give an example of how this data dependency management works, say you have 4 buffers, A, B, C, and D, and you have these 3 command groups. So each of these command groups executes a kernel, perhaps on a different device, perhaps on the same device, either way. And then the first command group reads from buffer A and writes back to buffer B. Second one also reads from buffer A, writes back to buffer C. And the last one reads from the results in buffer B and buffer C, and then writes it back to buffer D. Now, you have 2 command groups both accessing the same buffer A, but because they're only reading from it, the SYCL runtime knows that they can be accessed concurrently because no one's modifying it. However, when you come to run command group C, the third kernel, it knows that it's reading in from these 2 buffer B and buffer C, and these are being written to from other command groups, which means it has to wait until those are done. So the runtime implicitly creates this task graph for you, and all of the sort of management of these kernels is done by the runtime automatically, so you don't need to worry about it. So so the benefits of having a model like this means that you can forget about the low-level management of data and kernel execution, which you normally have to do through like event management. And it means that you can modify and change your kernels very quickly without having to worry about that. Just describe your kernels in terms of the data that it depends on. It also allows the runtime to do a lot of very clever things in terms of perhaps prefetching data that it knows you're going to be accessing later while it's still doing a computation on a different device, or leaving data on the GPU if it knows that you might well use it later. So if you've not asked for it back, it may just leave it there because then it saves in unnecessary copies. Okay, so the last part is I'm going to take a look at using the SYCL programming model, how you would write a parallel reduction. So for those of you who don't know, reduction is essentially like an extended accumulate. Effectively takes a number of elements and reduces it down to a single one using a binary operation. So C++17 introduced the parallel algorithms. And one of the main differences between the parallel algorithms and the standard algorithms is that the parallel algorithms are unordered, meaning that they can be parallelized. And the C++17 parallel algorithms also introduced these execution policies. So there's 3 main execution policies. There's sequenced, parallel, and parallel unsequenced. Sequenced essentially means that the order of instructions can be unordered, but they're all run in the same thread. So there's no option for parallelism. The parallel execution policy allows them to be reordered but run in multiple threads. So it allows you to parallelize but not vectorized. And then the paralyze unsequenced has the additional requirement that the instructions are allowed to be interleaved. So this allows SIM devectorization. But I'm not going to go into the parallel algorithms too much. For those of you who are interested in the parallel algorithms, there's a great talk from Bryce Livesey and Lelbach a couple of years ago at CppCon 2016. It's a very, very good talk, so I would check that out if you're interested. But I'm just going to look at one of the algorithms in particular, and that is accumulate and then reduce. So the original accumulate, so it takes the input iterators, first and last, so the beginning and end, an initial value and some binary operation. The binary operation is optional because the default is just a plus operator. And the standard requires that you take the initial value, then iterate over each element in that range and perform the binary operation on each one in turn, in order. The problem with this, so this would end up looking something like this. So you have all of these input elements, and then you perform the binary operation on each one in order. So if you put in these values, you end up with something like 72 there. Problem is, with the in order part, because it's in order, every single one of these operations is dependent on the previous one. So there's no option for parallelism. There's no way to parallelize it because you can't run anything until the previous one's been run. So then, this is where reduce comes in. So reduce is effectively the equivalent of accumulate in the parallel algorithms, but with the option for being unordered. So the first thing that changes is that it takes this execution policy, which is optional. But the main difference is this gsum. So the gsum describes how the reduction can be performed. So I won't go into this in great detail. Bryce's talk talks about this in much more detail. And the main thing to take from it is that gsum means that all of the elements of the range can be reordered in any order, and the binary operations can be grouped together in any order. So you could do like a hierarchy in any order of binary of the operations. So that means that with reduce, you could still write it like this in the same way that accumulate was, but you could also write it like this. So the difference here is that you now have only, even for the smaller number of elements, you only have 3 steps now instead of the 7 you had before, which means that you can run multiple operations at the same time. So if your system has the concurrency that can let you run multiple operations at the same time, you can get a lot of performance out of that. And if you have something like a GPU, which has thousands of processing elements that can run in parallel, then you can run thousands of these operations at the same time. So if we do the same thing again, we put in some values, add them up, you get 72 again. Same as the original. But there is one caveat to reduce the unordered algorithm. As if, say, you want to do a minus instead of a plus. You reduce that, you end up with 12. You reduce it with the other algorithm, you end up with 36. And if you do any other ordering or grouping of these operations, you're likely to get a different result. And that's because, due to the requirements of gsum, gsum allows the algorithm to be unordered, but it also means that the binary operation needs to be commutative and associative, which means that the binary operation has to be such that changing the order of the operations or the grouping of the operations can't change the result. So this rules out floating point operations and integer divide and minus operations. So it reduces what you're able to do. So you have to be careful about the binary operation that you use in your reduction when doing using this unordered algorithm. So now that we have this algorithm, how would we parallelize this on a GPU? So the first thing to know is that you want to take advantage of as much of the hardware as possible. And GPUs have potentially thousands of processing elements. And we saw before the best way to do that is to reduce dependencies between your operations. So you want to structure your algorithm in such a way that you can do as many operations in parallel as possible. And you also want to take advantage of local memory because the latency is a lot lower in accessing local memory. So here's a sort of high-level overview of how this algorithm would look. So say you have a number of input elements in global memory. And, the important thing to note is that due to the way a reduction works, is that at every stage of the reduction, the next stage is going to be dependent on the results of the previous one, which means you need barriers to synchronize to make sure that the previous results are done. And you don't want to use a kernel barrier because that's going to be really, really inefficient. You want to use a local barrier in the kernel. So you want to distribute all your data into local memory. So essentially what you want to do is you want to take all of your elements in global memory and distribute them into chunks the same size as your work groups. And then have each work group calculate a partial reduction. So each work group is going to take a chunk of the data and reduce it down to a single element, and then it'll assign it back to global memory. And then if you only have one result, you're done. If you have a number of results, you have to continue and go on again. And the important thing to note here is that at each stage of the reduction, effectively what we're doing in this algorithm is splitting the elements in local memory in half. And each element is taking its own value and the equivalent value on the other half and performing the binary operation. So you're essentially taking the second half and folding it into the first half using the binary operation. And then you're left with a number of elements of half the size, and you keep iterating down until you've only one left. So we're going to show how this would look in SYCL. So we start off with, we have the standard reduce prototype. Here taking a SYCL execution policy. Important thing to note here is that it's assumed that the iterators are contiguous, so iterators contiguous memory. The reason for that is that when you're copying data to and from a GPU, it has to be contiguous blocks of memory. And if you have, say, forward iterators or random access iterators, you then have to put it into a form where it's contiguous before you can copy. And that can be quite inefficient. So something like a vector or an array would be much more efficient here. So the first thing we do, so as we mentioned earlier, SYCL separates out the storage and access of data using these buffers and accessors. So the first thing we do is we create a buffer of value type and one dimension, and then pass in the input iterators, the begin and end. So this creates a buffer that is managing the data that the user has passed in. The next thing we do is we do this set final data. So this is quite an important thing. Effectively what this does is it tells the buffer not to copy back any results to the original host pointer. And that's important because the reduce algorithm is non-modifying. So the original input value shouldn't be modified. So normally the way in SYCL, the way buffers work is they synchronize on destruction. So buffer manages the data during its lifetime. So when it's destroyed, it copies the results back to the pointer that you gave it to. In this case, that's not happening because we specified set final data to null pointer, so we told it not to. But generally, you would use a buffer when it's destroyed, it copies back to the address that you created it with. The next thing we do is we create a queue. A queue is used to execute work on a device. In this case, we want it to be a GPU. So in SYCL, devices are selected using this thing called a device selector. And a device selector is effectively a function object which describes some heuristic for picking devices. So in this case, we use a GPU selector. A GPU selector basically looks through all the devices in the system and finds a GPU for you. The next thing we do is we need to identify the size of the data set that we want to execute over. So in this case, so we just do the distance between the two iterators. The next thing we need to do is we need to find out from the GPU that we got, what is the maximum size of the workgroup, so to use the workgroup efficiently. So here we simply ask the queue for its device, and then we ask that device to give us some info. So there's many different things that you can query from a device. There's many different properties devices can have. Here we're just querying what is the maximum workgroup size that device can execute. So the next thing we're going to do is, as we mentioned before, that each stage of the reduction, each reduction kernel will return a partial result for each workgroup. So that may be one value or it may be many. So in the case where it's multiple more elements, you have to iterate over it until you're down to one element. Now this might not be the most efficient way to do it. It's sort of it's a very general reduction. There are other ways to do it. You may want to, for example, after you do your first reduction, you're left with like 32 elements. It's not always going to be worth it to spin up another GPU kernel for those 32 elements. It's probably more efficient to just do it on the host. But this is a very generalized reduction. There are definitely more optimizations you could do. So the next thing we do is we create a command group. So as I mentioned before, command groups are effectively the objects which describe a piece of work that you're going to do on a GPU. So it describes kernel function that you're going to run, the ND range, and any dependencies of data that you have on that. And the way, in SYCL, the way you describe a command group is you call submit on your queue and you pass in a lambda function, which takes a handler parameter. And the handler effectively tells the lambda what you're submitting to. So it's a handler to the queue. So the next thing we do is we want to identify for this kernel invocation what the global and local workspace is going to be. So what the global and local ranges are. So the global range is effectively just the data size. So you want your global range to be every element that you have. Local range is going to be the minimum between the data size and the workgroup size. Because you don't want to be any higher than the workgroup size. You don't want to put more on the workgroup that can manage, because if you try to, you're going to try and allocate too much memory and your device isn't going to be able to support it. So you have to limit it to what your workgroup can support. The next thing we do is we create an accessor to this buffer that we created earlier. You do this by simply calling getAccess. And we specify here that we want read-write access because we want to be able to read in the input and then output the partial reductions that we got out of it. Next thing is we create a local accessors. So local accessors work a little differently. They allow you to allocate memory in local memory per workgroup. So effectively what we're doing, we're creating another local accessor of value type again, one dimension again. It's read-write, because you want to be able to modify it, read from it, and write to it. And you have this target local. We pass into that, we don't pass in a buffer, instead we pass in a size. So effectively what this does is it creates, in each workgroup, group's local memory, it will create a number of elements of value t type based on the size of the workgroup. So it creates one element of allocates one element of memory per value that you want to have in your workgroup. So the next thing we do is we create this parallel for. This is what we use to define the actual kernel function that's going to run on the GPU. So this takes two parameters, the first being an ND range, which is made up of just your global range and your local range. The next is a lambda, which describes the function that's going to run on the GPU. And this takes a parameter of ND item. So ND item reflects the information that we were talking about earlier, like the IDs and the ranges, reflects the space that you specified with ND range. So ND item is what you use to get the global ID and the local ID and the group ID of the current iteration. One important thing to note is that when you call parallel for in SYCL, you do have to specify a template parameter. So the reason for this is that in C++, lambda functions are anonymous. They don't have a type, which means different compilers are free to give them different type names. And so we provide a named type because it's associated with a lambda, which allows portability between different compilers. This is what allows you to compile with any host compiler and a SYCL device compiler. So it's a requirement for portability. So now that we're inside the kernel, this is what's actually going to be run on the GPU. First thing we do is we copy all the data from global memory into the local memory of each workgroup you want to execute. So essentially we get the global ID to index into the global memory, and we get the current local ID for where you are in each workgroup, and then you just copy and assign it into your local accessor. And then we add a barrier. And the barriers, the workgroup barriers here, just to make sure that before your workgroup continues, all of the data has been copied into your workgroup. The next thing we do is we create this loop that effectively loops over the size of your workgroup and halves it every time. And every time it halves it is finding the midpoint. So remember we said that we were going to take all of the elements from the right-hand side of your data and then fold them into the left-hand side. So we create a midpoint every time we iterate down. So say you start off with 32 elements, midpoint would be 16. After that reduction is complete, you're left with 16 elements, the midpoint would be 8, and so on until you get down to 1. The next thing we do is we put an if statement to say that we only want to work on the first half because we're only assigning elements on the first half of the data. The second half is just being read from. And then finally we do the actual reduction operation. So here we use the local ID to access So the current ID, so we take the element at the position of the current ID in local memory and put that into the binary operator with the equivalent ID on the other side of the data, so offset plus your ID. And then you put them into the binary operator, and the result is then stored into the current element of your ID in local memory. So this is the act of folding one side into the other. And then we add in a barrier after each loop to make sure that each stage of the reduction is complete before we move on to the next one. And then at the end we have, so once once all of the loops are finished, we then will be left with a single reduction. So each work group will have a partial reduction in that value. And then the next stage is we get local ID to access that element, and then we want to copy that back to global memory. The interesting thing here is when we're accessing global memory, we use the group ID. So the reason for that is that, say if you had 16 work groups executing, each one of them generates a partial reduction. You want to store them back into global memory contiguously. So a good way to do that is to take the group ID, because if you have 16 work groups, group IDs are going to be 0 to 15. So you use that ID when you assign back to global memory, you're now assigning all of your partial results in a contiguous block of 16 elements, which can then be used in the next iteration. And that's why we divide the data size by the workgroup size for the next iteration. So you'd be left with the 16, and then you would iterate over it again. And then once all of the outer loop is complete and you're left with a single value, we create the host accessor. So the host accessor gives you immediate access to the data on the host. So generally this will then trigger a copy back from the GPU, the results. And we only need read access, and then we pass the value of that final reduction into the binary operator with the initial value, and then we return the result, and then that's the algorithm complete. So you've returned the reduction of all of those elements. Now, there should be some time for afterwards. If anyone has any questions about this, we can go back to it. I can also make the code available to anyone if they're interested. I understand it's quite a long algorithm. So finally, I'll look at some of the ecosystem projects for SYCL. So there's a couple of implementations of SYCL. So at CodePlay, we have an implementation called CppCP that actually released the 1.0 release last month. It's 1.2.1 SYCL compliant. There's also a work in progress open source implementation called TrySYCL. It's a community open source project. And we have a website, sycl.tech, that's quite good for keeping up to date with news. There's blogs from CodePlay as well as other companies working with SYCL, information from the Khronos group and updates, that kind of thing. And there's several other ecosystem projects that we're working on. So there's an implementation of the C++ 17 parallel algorithms using SYCL. We have a vision library called Vision CPP. We have a BLAS library, SYCL BLAS, and we also have TensorFlow and Eigen ported to SYCL. And as a quick plug, if anyone is interested or likes what we're discussing today, there will be a post-conference 2-day class with myself and Michael Wong. We'll be covering this kind of thing as well as a lot more. So we look at parallelism on CPU and GPU. On the GPU side, we're using SYCL. Okay, so in conclusion, we looked at how to write a reduction for a GPU using C++, using SYCL. We looked at how SYCL programming model let us do this and how that maps to the GPU architecture and the GPU programming model. And we kind of went into why you would want to do this. So if you enjoyed it, thank you very much for your attention. So I think I have about 10 minutes left, so if there's any questions.
Is SYCL tied to a specific version of OpenCL?
So the question was, is SYCL tied to a specific version of OpenCL? So it is. So the current version of SYCL is 1.2.1, which is tied to OpenCL 1.2. Future versions of SYCL are ongoing, and they will support additional features of OpenCL from later versions. Okay. I think, do I go to microphone for questions? Oh.
So your accessors and permissions system, you showed read and write, but obviously there's a much richer system of how do I say it? Set of access permissions you could envision that involve, commutative operations that involve partial writes overlapping with partial reads, etc. How flexible and extensible most importantly extensible, is the SYCL permission system?
So the question was how flexible is the accessor permission system in SYCL, and whether it could support additional, more specific access patterns in the future. So at the moment, there's quite a few different access patterns in SYCL. So you have like read, write. There's also discard options, which specify whether or not you want because generally when you have an accessor, it'll copy in the original results. So sometimes you might want to copy the data in, only write to a part of it, but you still want the values that were in the other part to stay there. So that's the general case. You have discard options when you don't care about that. So discard basically means that it won't copy anything to the GPU because you want a clean slate. You don't care what was there originally. It's definitely flexible for future operations. I can't really say much about what's ongoing, but it's very customizable, and future versions of SYCL will likely have other options for how you access memory to support new features. Will that answer your question?
Yeah, thanks. Thank you.
Hi, my question is probably a continuation of the first one. So, whose responsibility it is to support SYCL? For OpenCL, for example, it was the responsibility of the driver authors to create a compiler for OpenCL to their particular hardware. And for example, when NVIDIA said we're going to go ahead with CUDA, and they just stopped supporting OpenCL. So I think NVIDIA support like OpenCL 1.1. And does SYCL sort of use OpenCL internally? And by using, for example, OpenCL 1.2, does that mean that NVIDIA devices are off the table for SYCL, for example?
Okay, so the question was, so whose responsibility is it to support SYCL? Whether or not you'll be able to use, for example, NVIDIA. So generally, so SYCL is based on top of OpenCL, so it uses OpenCL. And for example, our implementation could be CPP. It generally uses the SPEAR binary format. So generally the way SYCL works is that SYCL can support any platform that has OpenCL in some binary format that can be loaded. And often that means SPEAR?
But not SPEAR V?
SPEAR or SPEAR V.
So if it supports Vulkan, it will support SYCL?
Potentially, yeah. So it could either be SPEAR or SPEAR V or some other hardware-specific binary representation. For example, CppCP currently has experimental support for NVIDIA hardware through PTX. There's only partial support, but it doesn't have to be limited to SPEAR or SPEAR V. It can be any different binary format, as long as it's supported by an OpenCL implementation.
Okay.
But that'll be up to the implementation of the SYCL implementation to support. So the SYCL implementation can support more, but it's up to the implementation. So we support, I think CppCP currently supports Intel, AMD, ARM, and NVIDIA hardware, with also support for the Renesas RCAR hardware as well. So it can support a large range of things, as long as the hardware underneath supports OpenCL.
Right. Thanks.
Thank you.
Hi. So where's the overhead for the actual compilation of that OpenCL kernel?
Sorry?
So that OpenCL kernel will need to be compiled down. Is that in that submit function?
So the kernel. So was the question that where's the SYCL kernel function compiled?
Yes.
Okay. So I didn't really touch on this much in this talk, so I didn't really have the time to fit it in. There was a previous talk, the CppCon a couple of years ago, where we showed this in a bit more detail. The way it works is that you have the same source file as compiled by two compilers. It can be a single compiler with a driver that dispatches to two. But the way CppCP works is you have two compilers. The first is a device compiler, which basically extracts the code. So the part that you see here in the parallel for, that is extracted and compiled for down to SPEAR or PTX or some other format, and then run through OpenCL. It's also compiled by a host compiler. It can be any standard C++ host compiler. It could be Visual Studio or GCC or Clang. And then that hooks in with what was generated by the device compiler. So it's offline compiled and then run through OpenCL by the SYCL runtime.
Thanks.
Okay, thanks.
I'm excited about using this, or at the higher level you showed with the reduce example. I wonder if you have do you have a full set of parallel STL stuff available. Is it complete?
So the question was, do we have a complete set of parallel algorithms? So there's the SYCL Parallel STL project, which is an open source project. The Khronos group, which is worked on by Codeplay as well as some other people. It has, from what I remember, it has most of the parallel algorithms. I think there's still some that need to be implemented, but they're mostly there. I could take a look and I could speak to you offline and give you a more accurate list of which ones are supported. But the majority of them are supported. Thanks.
Hi there. So the example that you showed was, at least in my opinion, fairly low level. I could do a mental mapping back to like CUDA. In previous interviews with Christopher DeBella, I believe is his name, yep. He'd mentioned facilities, and perhaps this is the parallel STL you mentioned, but facilities for doing lazy range computation in like a range v3 or a thrust style. Is that the parallel standard algorithms you were describing, or is that a separate product, or is that a development project?
So the question was in reference to, I think you were referring to the Parallel Ranges project. So this is actually a project that Codeplay has been working on with some other collaborators. It's not the Parallel STL that you have in C++ 17. It's an extension of that. That's not standardized yet. It's still a in progress project, where effectively what it means is that you have a ranges based solution. So you have these lazy ranges, really lazy views that can compose algorithms together and then compile them into a single kernel, which is run on a GPU. The benefit of that is what we call kernel fusion. The benefit is that often the overhead of launching multiple kernels is quite high, and sometimes it can outweigh, if you have very, very small algorithms that aren't doing very much, sometimes the overhead of copying data around or invoking kernels can sometimes outweigh the benefit. And that's one of the problems that we saw with some of the parallel algorithms. So the Ranges project is the idea is to use kernel fusion to do multiple operations together, fused into a single kernel, and then run on a GPU. So it's to make the parallel algorithms more efficient than they would be already.
Yeah, you mentioned this emulation layer, that if there is no GPU, the code can still run, and that this is for debugging purposes. But could this also be for running actual code? That otherwise I have to duplicate all the code. I have to write a version for the native CPU, and if there's a GPU, I write your SYCL code. Or could I just write only the SYCL code that runs near natively also on the CPU? Is that a goal?
So the question is whether you could use the host device, the emulated device, as a target itself, not just for debugging.
Yeah.
So yeah, that's entirely possible. The requirements are only that it support the underlying OpenCL programming model. Originally, it was envisioned for debugging purposes, but there's no reason why that can't be a full, very efficient, performant implementation. So yeah, that's definitely possible.
And then beyond being possible, is it also a goal of the SYCL suite to support that in the near future? Or?
So the question is that a goal to support that in the future? Do you mean? So yeah, that would be supported at the moment. So often, so I think the reason that we saw it as a debugging tool is often when you have an OpenCL implementation, you'll often have a CPU implementation that would be like an optimized implementation for running on the host. So you'd use that. But in the case where that isn't available, the host device could serve as an efficient implementation. It would be up to the SYCL implementation to do that. But yeah, there's no reason why you can't do that. I think I might have time for one more.
So, is there any possibility for the developer to decide whether a piece of, we'll call it work, goes either to the native CPU or another device, or is it always SYCL making the call, saying I'm either going to always send this to the GPU or CPU, or do you have kind of dynamic dispatch so that we can take a look at a piece of work and decide this is good enough to be run on the CPU, or this is good enough to actually, be thrown at the GPU because it's intensive?
Okay, so the question was, so who can the developer make a decision about where the work is executed? So yeah, definitely. So the SYCL queues effectively, well, they'll always execute work where you asked it to, unless it encounters a problem, which there's an option that can fall back to another device. That's one of the features of when you construct a queue, you can specify a fallback. So it's like in order to ensure that it'll always execute. But generally, a SYCL queue will always execute where you asked it to. We didn't want to have the SYCL runtime make any clever decisions about where to run things, because that can often involve a lot of, say, offline static analysis and that kind of thing. So we wanted to leave that as to a layer above SYCL. So you could write a layer on top of SYCL that queries the devices that you have and does things like load balancing. For example, there's an execution policy in the SYCL Parallel STL project that does just that. So it takes two different queues and it can do load balancing, efficient load balancing of separating a task between CPU and GPU. So for example, it could do a reduction or a sort split across the CPU and the GPU at the same time to make it even faster. Thanks. I think I'm out of time. Okay, thank you very much.